In this video, I'm going to look at two more examples of hypothesis testing without finding the critical region. In the first one, we're going to look at an example which uses the binomial where p is greater than 0.5. A footballer scoring penalties with a probability of 0.8. In 20 penalties, he scores only 13 times. Is there any evidence at the 5% level that the footballer is losing his form? Well, we start as normal with the null hypothesis, H0. That is that the status quo is being maintained, p is equal to 0.8. The alternative hypothesis, what we're going to conclude if we reject H0, if the footballer is losing his form, then p is less than 0.8. This tells us that we have a one-tail test, and we're doing it at 5% significance. Well, suppose that x is the number of goals from 20 penalties. Then we're looking at x as binomial 20, 0.8. Now our tables only go up to 0.5, so we must consider y, the number of misses. In obviously 20 penalties. Then y is going to be binomial 20, 0.2. Right. The test statistic is x equals 13, and so we want the probability that x is, and we're down the bottom end of the distribution, the mean is 16, 13, are we worse than or equal to 13? That means that x could be 13, 12, 11, etc., down to 0. Y therefore could be 7, 8, 9, up to 20. And so this is going to be the same as the probability that y is greater than or equal to 7. Looking in the tables, this is just 1 minus the probability that y is less than or equal to 6, which is 1 minus 0.9133. And therefore, as this is what we're looking for, the probability that x is less than or equal to 13 is equal to 0.867, which is 8.67%, and our significance level is 5%, and therefore this is not significant. That is because 8.67% is bigger than 5%. And that we can see if we look at the picture. There is the probability that y is greater than or equal to 7, or x less than or equal to 13 is 8.67%. My 5% line would lie on the left of that, because 5 is less than 8.67, so it's going to be somewhere over here. and therefore the test statistic, which is y equals 7, does not lie in the critical region. And we can accept H0 and conclude that there is evidence that the footballer has not lost his form, or that the probability of scoring from a penalty is not less than 0.8. In the second example, we're going to use the Poisson distribution. If we think of cars arriving at a motorway filling station at a rate of 3 per minute, that is the normal situation. On a Tuesday morning, 10 cars arrive in 2 minutes. Is there any evidence at the 5% level of significance that this is an unusual morning? First thing to notice is that we're just asking whether it's an unusual morning. It would be unusual if too many cars arrived or too few. In other words, we're going to be looking at a two-tail test when it comes to it. Let's start off with our null hypothesis. H0, nothing has changed. Well, we're going to be looking at a Poisson distribution arriving at a constant rate, singly and independently. That makes sense. So we're thinking of a mean of 3. That is per 1 minute. It's quite acceptable, and in many ways I prefer it, to use H0 lambda equals 6 if we're thinking of the 2-minute periods. So you can use either form of the hypothesis. Lambda is 3 or lambda is 6. H1, the alternative hypothesis, unusual. It's going to be unusual if lambda is not equal to 3. It's going to be unusual if lambda is not equal to 6. In this case, we have a two-tail test. 5% level of significance. Which gives us 2.5% in each tail. Okay, we've now set up the situation, and we're in a position to do the test. Suppose that X is the number of cars arriving in a 2-minute period. Then X is going to be a Poisson variable with mean 6. The test statistic is X equals 10. Well, 10 is the test statistic. The mean is 6, so we're looking at the upper end. We're looking at the upper tail. So we want to see what happens if we're looking at probability X is greater than or equal to, never forget the equals, 10. Well, this is very easy from our Poisson distribution tables. We can just look that up. That is 1 minus the probability X is less than or equal to 9. That's 1 minus 0.9161. And therefore, we've got that the probability that X is greater than or equal to 10 is 0.839, which is 8.39%, and that is bigger than 2.5%, and therefore not significant. This means that we can accept the hypothesis H0 and conclude that there is evidence that it was not an unusual morning, or that there is evidence that the rate at which the cars were arriving at the filling station was not 3 every minute. 8.39% is bigger than 2.5%. That means your figure x equals 10 cannot lie in the 2.5% area. You need to be able to understand that easily. I have also drawn a graph so that we can see it. And in this case, we have the probability that x is greater than or equal to 10 is the area to the right of the green line. That is over 8%. So when I put the blue 2.5% line on, it must be on the left of the green line, which means that the value x equals 10 cannot lie in the critical region. We don't have to work out where the critical region is. We just know that 10 cannot be over here.